Hello, my name is Brian Zadwarny. I am talking about CSCI 185 Big Data Analytics, my final project, case study in medical informatics and continuous blood glucose monitoring. Big data is new to medicine. Doctors are slow to adapt. They really want to be careful about what they're doing, and in many cases there's a phobia for new technology, so they're slow to adopt anything. There are two new regulations out. In 1996, they came out with the Health Insurance Portability and Accountability Act that talks about how we store digital information, how we store patient records, how we transfer the records, and set some penalties. The Health Information Technology for Economic and Clinical Health came out in 2009. That's known as the HITECH Act. That sets incentives and provides money for people to research and find ways to use information technology in medicine. Unfortunately, HITECH also raised the penalties that HIPAA set for misusing or misplacing data. We're going to talk about four major sub-areas in big data medicine: patient data warehouse, predictive medicine, wellness medicine, just-in-time medicine. Patient data warehouse. So this is all of the information about you that the doctor has. Your electronic health images records, your digital images in the DICOM format, the PACS system, which is the database that holds the DICOM images, and then all the other stuff that they record about you: EKGs, blood pressures, O2 readings, glucose measurements, which we're going to talk about a little bit more, the blood work they record on you. All this data is stored and saved. But who owns it? It's information about me, but do I own it, or does my doctor own it? And what happens if my doctor wants to talk to a specialist? Or what happens if I move and change doctors? Who pays to maintain all this information? What happens if I move? Who pays to move it? I can't just pick up a computer and move it cross country. What formats do we use? The internet's 20, 30 years old. They've been working on this internet standards. Well, what about medical standards? Who sets the standards and who enforces these? And then HIPAA and HITECH set some pretty hard penalties for what happens if there's a breach with somebody's data. If somebody hacks in, if a laptop's stolen, it's talking about millions of dollars worth of fines for breaking HIPAA. There are way more questions than there are answers when it comes to HIPAA and HITECH. So predictive medicine. In the past, doctor asked you about your patient history. My grandfather had heart disease and my mother had cancer, and he says, okay, well, that's a risk factor. We got to watch you for these things. In the future, we're actually going to look at your genetic code and say, hey, you've got the gene for Alzheimer's. Maybe we need to start watching you for Alzheimer's. Or you've got the genes that lead towards blood cancer, so we're going to monitor you for the signs of blood cancer. Wellness medicine. In the past, you would say to the doctor, yeah, I drink smoke, and when I was in college, I borrowed needles from my friends. I had a lot of fun in college, a lot of girlfriends, and he would kind of use that to say, okay, well, we got to work on this. In the future, we're going to actually be able to unlock patterns that say, you're in a high-risk group. We've seen over the last 5 years your blood pressure has increased by 10%, and we now identify that as a high-risk group. Once we know you're in a high-risk group, we can then get you moving towards healthier behaviors or on the right medicine sooner rather than later when you're already in the danger zone. Things like Google flu trends can actually read the news and read tweets and identify where the flu is getting bad or identify diseases coming up around the country. And, this medical internet that's coming around, 20 years ago, there could have been a bird flu outbreak in China. We would never know. Now, by the time there are 4 patients with the bird flu, we're getting word over here in America. So, just-in-time medicine. This is about spending as little time and as little effort taking care of the patient as necessary. More specifically, it's finding the right amount of care to give a patient. We're talking about less well visits, more targeted visits before you get sick. How long after surgery should a patient stay for observation? Do we need to stay for 5 days, or can we get away with 3? That frees up a bed for a sick patient. When should the patient return for a checkup? We don't have enough doctors. We got too many patients, and as our parents are getting older, they need to see doctors more. So we can look and study more about which medicines are helping and which medicines aren't helping so much. We can figure out what is the right dosage for the patient. And as we're taking more and more drugs, we're able to identify the adverse drug interactions quicker, because instead of one doctor with 20 patients taking these 2 drugs, we can put all the patients in the country together and identify a lot sooner that, hey, these 2 drugs working together are actually do more damage than they do good. So we're going to do a study in just-in-time medicine. We're going to look at continuous blood glucose monitoring. These devices are worn for up to 2 weeks at a time, take one reading every 5 minutes, and that's about 4,032 readings over a 2-week time. If a doctor has 250 patients, that's over 1 million data sets. Right now, they're only worn for 2 weeks. The FDA is working on approvals for allowing patients to wear these for longer periods of time. The longer patients wear it, the more patients they're going to have wearing it, and the more doctors are going to have to spend analyzing this data. So we need to come up with an automated system to analyze this data. The next step for continuous glucose monitoring is taking these readings and taking the insulin pumps that already exist, blending them together, and actually letting them talk and figure out when to give the patient insulin instead of the patient just guessing at how much insulin to take. This means when you have that chocolate cake, your body knows, hey, that's more sugar, I need to give more insulin. In a healthy person, this all happens automatically. In a diabetic person, the insulin pump or the person just gives themselves the same amount of insulin every day, regardless of what their body's doing. So we're going to look at analyzing the results for 250 patients. Our data is not sorted, so we're going to have to sort it. We're going to calculate average, maximum, and minimum blood glucose level, and then we're going to identify patients who are in a danger zone. Our file structure is here. You've got 3 folders. FP has the full 250 patients in a file called tests. In file FP1, there is small test, which is just 2 patients worth of data, and FP2 is only about 25 data sets. FP1 and FP2 folders allow you to just run the files quicker. You don't get the full data set, but you do get to run the code and play with the code if you want to try and break it or change it. I've given you a bunch of different pig scripts. The big one is fp.pig. That's all the code, all the outputs. It's all programmed to automatically run. You don't have to tell it any inputs or outputs. It knows what to do. Bad sort example shows the bug in pig. Sorted data 2 shows how I sort the data. ID values calculates the average, min, and max for each patient over the 2-week period. ID values high identifies patients who have a blood glucose reading of over 150, which is the danger zone where we would have to identify the doctor. And the final daily result looks at an average reading for each day instead of over the 2-week period. There's also a final project folder that has all the results that I calculated. If you don't want to run the scripts yourself, you can see my results. Setting up the environment, we're using Cloudera Linux with pig installed. It's what we did for homework 7, so all the students should have this already. You're going to extract the data and put folders FP1, FP2, and FP3 in all the pig scripts. You want to copy FP, FP1, and FP2 over to your Hadoop file system. And then all you have to do is from the shared folder or wherever you put your pig scripts is just type pig and the name of the script. They're all programmed, they'll all do their thing, and then you can see the outputs. The input data format is comma-separated list. You've got the patient ID, the reading, the change from the last reading, which is called delta, the date of the reading, and the time of the reading. All of these shorter scripts, at the bottom of them down here, you can see what you get out if you were to type illustrate and the last tuple that you created, and then it also shows the tail of the file that gets created. Our first step is to sort the data. You know, this data is randomly put in there. Wherever the machine got it, it stored it. So what we're going to do is we're going to load the data into the tuple A. Then we can't sort on date and time because they're car arrays. So what we have to do is split them into integer values. And then we should be able to order them or sort them based on their integer values. But there's a problem. See, pig lies. An int isn't an int, it's a string. What I mean by that is when you try and run a command such as order B by day, when I illustrate B, you can see that day is an integer value. But you run this command right up here, you get a class cast exception. Java lang string cannot be cast to Java lang integer. Apparently there's a bug in Hadoop and pig where it says it's an integer, but it's really not. So to fix that, I actually store B into a temp file, then I read it back into C, the tuple C, and tell C they're integers. From then on, everybody's happy. So once I read the data into C, I order the data by ID, year, month, day, hour, and minute, and call that D, and I store that D into sorted data 2. All of my storing I'm storing is comma-separated list. If you run sorteddata.pig, you will save it in sorted data 2. If you run fppig, the data is going to be stored in sorted data. And here are your tuples and the results. So now we want to calculate the average by patient. So all we have to do is start with C and create C. From C, we're going to generate ID reading, which is just the ID and the reading. Then we're going to group by ID. We're going to calculate average, max, and min for each group. And then we're going to store the values. As you can see here, where we start with C, we come out with our ID reading, which is just a list of ID and reading. When we group it, we come up with the group is the ID value, and then the tuple is all of the readings. And then when we calculate our average, we come out with our patient ID, the average, the maximum, and the minimum value. Here's our results. You can see it's the same comma-separated list. You've got your ID, the average value, the maximum value, and the minimum value for each patient. Now the doctor says, hey, we want to find patients who are in the danger zone. So we want patients that have results over 150. So we're going to take in that ID values that we the filter ID that we started with at the end of the last script, and we're going to filter it for all values with a maximum over 150. We're then going to sort that by decreasing values so the sickest patients are at the top, and we're going to write that. As you can see, this is what we did in the last script. We now have ID values. We're going to sort it, ID values high. Unfortunately, when I illustrate it, the example it had didn't have a maximum value above 150, but when you look at our results, there are 4 patients who had a maximum value above 150, and it identifies them. So the doctor says, well, you calculated the weekly values, or the values over 2 weeks. Can you calculate it by day? And you say, oh, that's easy. Unfortunately, you can see all the steps. I'm not going to be able to explain this to you, but it will be a good exercise for you to go through the code and see exactly what you're doing. So we're going to start with C. We're going to generate the ID just like we did the first time, but now we're going to generate it with the date and results to create the new date tuple called CDate. Then we're going to group by ID and date. We're going to calculate the average, max, and the min for each day group, and then we'll sort it. But wait, we can't sort on date because it's a string. So now we've got to generate the date, the year, month, and the day from C. We call that tuple full date. We get the distinct values, which is distinct full date. So instead of having 2048 values, we've got one value for each day of the week. We just join our distinct full date and our final daily, which is this and this together. We cut out the extra values because you're going to have a couple extra dates in there. We sort it using the order function, and then we cut out the values we don't need. We don't need to save month, day, and year. We just need the date value, and we save that to the database. So here we go with our final daily result. I'm not going to show you the code because it's just too much to show, and I don't have enough time. So right here we start out with C, which is just our rough datas. Now we have C date, so we have the ID, the date, and the reading. From there we group it by ID and date, and over here you've got your group and your reading. We make our calculations by ID, date. We calculate our average, our maximum, and our minimum. Then we get our full date, which we go back to C. We pull out the date, the month, the day, the year. From there, as you can see here, we're going to have multiple 111s with the exact same values. So when we calculate distinct, you see we've got 2 111s. When we go to distinct, we only have one of each. From here, we join final daily and distinct full date, and we come out with 2 date fields. We don't want to be passing that data back and forth to Hadoop, so we filter out one of the date fields. We order it, so now our data is in the correct order. We no longer need the day, the month, and the year, so we get rid of them. And then that's our result that we save to a comma-separated list for the doctors. Conclusion: big data is new to the medicine world. There's lots of chance to make things great. We talked about how we're going to analyze the data. We formatted it. We identified patients who are getting ill. And we talked about how in the future we're going to take these technologies and these techniques to generate an artificial pancreas.